Very good morning to one and all present here. I am Garpadasamy, working as an assistant professor at KSR College of Engineering. Today we are going to discuss VLSI design subject. So actually what we are going to discuss in this VLSI is, first unit is Verilog HDL. So in this unit we are going to discuss the hardware description language. Actually it is a key tool for digital design and simulations. Okay. So this is the thing we are going to discuss in this first unit. And in second unit we are going to discuss the VLSI fabrication techniques. In this unit we are going to discuss what are the fabrication process and what are the design rules which are used for creating the CMOS chips will be discussed. And in third unit we are going to discuss CMOS logic gate design and layout. This unit focuses on designing and layout CMOS logic gates. So here we are going to discuss the CMOS inverters and standard cell designs, what is transmission gate, pass transistor. These are the things we are going to discuss in this unit. And in fourth unit we are going to discuss the storage elements and dynamic logic circuits. Here we are going to discuss what are the storage elements available and what are the different dynamic logics or domino logics available. And in fifth unit we are going to discuss the test and testability. So actually from the first to fourth unit we are going to discuss about the integration process. In fifth unit we are going to test the chips what we have made. Okay, so this unit addresses the importance of testing in VLSI design to ensure the functionality of chip. So this is the fifth unit, and now I am going to give a small Verilog HDL. So first of all you want to know what is meant by Verilog HDL, right? It is a hardware description language. It is a language used to describe, model and simulate digital systems. Okay, so this is the definition for our Verilog HDL. Actually HDL is divided into two. One is VHDL and the other one is Verilog HDL. So here we are going to discuss about the Verilog HDL. Verilog hardware description language. Actually it is a textual way to represent the hardware designs at various levels of abstractions. There are three levels of abstractions are there. One is behavioral model, data flow model and structural model. So these are the three levels of abstractions we are going to discuss in this Verilog HDL. Actually this Verilog HDL is widely used in the design and verification of the digital circuits. So you may know that you might have studied number of digital logic circuits, okay, for like AND gate, OR gate, XOR gate, like that. So we are going to discuss how to represent these hardware circuits in the description. Actually we are going to represent it in the textual way, right? That is the thing we are going to discuss here. And here we can design the FPGA, field programmer gate arrays, and the application specific integrated circuits. Using this we will see one by one what are the various levels available here. So before going into that we are going to see the history of Verilog. So actually this Verilog is introduced by Philip Moorby in 1983. So at Gateway Design Automation, this is the company which he worked in that. Through this company he introduced this Verilog, and the Gateway Automation is bought by the Cadence in 1989. Okay, so and this Verilog also had an IEEE standard. IEEE standard in 1985. December 1995 they got an IEEE standard. Okay. So then you want to know what is the difference between the Verilog and VHDL. I already told you that there are two different languages are available. That is two HDL languages are available. One is Verilog and the other one is VHDL. Actually this VHDL is developed by the US Department of Defense, and Verilog is created by, I already told you that, right, Gateway Design Automation. And this VHDL is uses a strongly typed syntax. Okay, so it is similar to that of the ADA language, ADA language, but the Verilog is similar to that of our C. Okay, so that's why we are going to see this Verilog, because it is the syntax of these Verilogs are similar to that of our C language. So then this VHDL is used for high level system modeling, but this Verilog is used for low level and gate level system designs, right? So this is the thing why we are going to Verilog rather than this VHDL. but both will support the design of VLSI, and this VHDL supports the rich set of data types, but in the case of this Verilog, it supports simpler data types. Okay, so this is the comparison between the Verilog and VHDL. So I would like to say about a simple thing about or basic thing about this Verilog. So the basic unit of this Verilog is known as module. Okay, so this, what is the purpose of this module? It is used to describe the functionality of the design. So for example, if you are taking the AND gate, we are going to describe the functionality of the design and states the input and output ports. What are the input output available? So this is the thing we are going to discuss in this module or describe in this module. Okay, for example, if you are taking a computer performs user defined computers. That is actually the functionality of a computer. And what are the input output ports available? Keyboard, mouse, monitor, printer, or some of the input output ports available. So this is the thing we are going to describe in the module, inside the module. This is actually the basic unit of this Verilog. Okay, so and this is the basic syntax for module description. How to describe the module. This is actually a programming language. We want to describe this like this. Module should be described like this, right? It should be declared like this. Module name. This is actually an identifier. This can be given by our own, right? And port list. What are the input output available? Okay, so here we want to declare the port declarations. For example, in C you will declare the data types, integer A, B, C, like that you will declare. So similar to the top, that here we want to declare what are the input output ports we are going to use. Okay, so then what are the variables? If you want any other variables, you can declare here, and the description of the behavior should be given here, right? So the describe, you want to describe the behavior of a particular circuit. For example, if you are designing the half adder, you can give the description of the half adder here. So then end module. Okay, so this is the basic syntax of that HDL, and as similar to the top of our C language, here also we can give single line commands. Commands can be given. The single line commands can be given using the two backslashes, and multi-line command also can be given inside of the star slash and slash star, right? So in between that you can give multiple line commands. So and the identifier, you know, right? It is a sequence of letters. It can be given by our own, right? Maximum of 1024 letters to be there for declaring this identifiers, and only one condition is that it should not that is, the first character must not be a digit. So that is the only thing you might remember when you are declaring or identify. Okay. Then what are the levels of abstractions available? What are the various levels of abstractions available? There are three levels of abstractions. One is structural level modeling, data flow modeling, and behavioral modeling. We will see one by one. What is structural level modeling? So it is actually described in terms of Verilog gate primitives. For example, you know AND gate, OR gate, NOT gate, etc. So these are all inbuilt gates available. If you are using these inbuilt gates to represent the structure of a circuit, so then it is called as structural level modeling. For example, if you want to describe the circuits, here we are having two AND gates and one NOT gate and one OR gate, right? So to represent this, here we are having NOT N1 of select. What are the input and output? So this inverter has two ports, that is one input port and one output port. So the input is select line and the output is select n hyphen comma n, right? So here we are going to represent the output comma input. So this is the way to represent this structure. Okay, so then we are having two AND gates, A1 and A2. So for A1 we want to represent what are the output, what is the output, and what are the inputs we are going to give. Okay, so as similar to the top, that for AND gate 2 we should give and OR gate. So here we are having in one OR gate. So this OR gate has two inputs, that is select A and select B, and output. So here we are representing like that, OR of O1 comma. So this is actually a module name, out comma select B comma select A. So out is an output and select A, select B, and select A as an input, right? So this is the way to represent or way to represent the structural model. Okay. So then the data flow modeling. The data flow modeling is used to specify the output signals in terms of the input signals. So for example, if you are having or if you are designing an AND gate, that AND gate might have a characteristic equation, right? So if you are representing the characteristic equation, so then it is called as, using the characteristic equation if you are representing, then it is called as data flow modeling. Okay. So for example, here this circuit is represented using this. Actually, if you are using this data flow modeling, the assign statement should come, right? Using this assign statement or assign keyword, it is actually a keyword. Using this keyword, you can represent this. Okay. For example, this circuit is given with this equation. Okay, well. Then the next one is that behavioral modeling. So if you are specifying the behavior of the design algorithmically, then it is called as the behavioral modeling. For example, here we are having a 2:1 mux. It contains the inputs A and B and one selection line and one output. So this can be given like this, right? So it can be represented based on its behavior. For example, if the select line equal to 0, so then output will be 1. So that is output equal to B. Output B will be selected, and else if select line equal to 1, then output A will be selected. Okay. So that's all about this. Thank you. Thank you one and all for the patient listening. Thank you.